Good evening, guys. Um, this is Engineer Ali on the line. Today I'll be explaining to you continuous slab spanning in one direction and likewise a two-way spanning slab. And please, I'll be using two PS code for this because I realized that one is having the IU still of FY to be 460, while another one is having um, 500 Newton per mm square. I think the latest one in the 6110 is having FY of 500 Newton per mm square. So I will be interchanging it, but before I will try and harmonize it so that it will be easier for you all. Now, as I said, when we're designing a continuous solid slab spanning in one direction, there are some things that we need to or conditions that we need to check for. First, in a one-way slab, we need to check the area of each bay. That is, this is a bay. If you have something like this is a bay. You can see it. These are your columns, and the bay must, let me say, the area of each bay must not be less than 30 meters square, and the life load should not be greater than 1.25 of your dead load, and the life load should not be greater than 5 kilonewton per meter square, excluding partitions. So these conditions have to be met before we move to the next one. So I said for the effective span is the basic span effective dead ratio is around 26:1, and you can see that in table 312 of your BS 8110. As you can see, in your page 37 of your BS 8110, you see this table here where you will select your moment for each of the support condition, maybe the span. This for continuous, and maybe if it is simple. So depending on what you are dealing with, then at first interior support and middle interior spans, etc., etc. However, for this one, this coefficient is include an allowance for a 20% reduction. I don't want to talk much about that. Let's go straight to the calculation, so you will see as we tackle the challenge. Now, let us say, for instance, we have this floor span, this 4-span slab, this span 1, span 2, span 3, span 4, and it's having a life load of 3 kilonewton per meter square plus finishes and ceiling load of 1.0 kilonewton per meter square. This ceiling load, you should know that will be added dead load, so it's very important. And your FCU is 30 Newton per mm square, while your FY is 500 Newton per mm square. So I have it this way: the center to center spanning 5 meters, and the distance apart is 7 meters. So how do we treat this kind of continuous one-way slab? So let us look at it this way. We first look at the basic span effective depth ratio, which is 26. Let me see if I can. Okay. Just open your BS 8110 and you will see it in table 3.9. You see it for simply supported. If it's rectangular section, you see it to be 20, and for continuous, you see it to be 26. So since we are treating continuous, that's why we're taking 26, and then the span is 4.5. We have 173. Now I want to try effective depth D to be equal to 140 mm. So the overall depth will be something like 170 mm. You first select a trial depth, then we'll check whether the depth will be able to carry whether it will be lesser than the, let me say, limit depth. So, but I will show us how we'll start everything from beginning to the end. And please take note, here we calculate the self weight of the slab, which is 170 times 24 times 10 raised to the power of 3. This 170 is this depth here, and this 24, that's this self weight of concrete. Now, if you can recall the other time, I told you that the total dead load will be, I said there's an added dead load of this 1 kilonewton per meter square. So that is what we have here, 1.0 plus this 4.08 to give us total dead weight of 5.08. Now we calculate the load per span, which is at 1.4 GK plus 1.6 QK. So if we do that, we have this we have 53.6 kilonewton per meter width, and then we go straight to, sorry, we check for the bending. Since the base size is greater than 30 meters square, the spans are equal, and the imposed load is not greater than 1.25 GK, then the moment of coefficient shown in table 312 will be used. This will be used. So now let us the first thing we try to do is we look at m to be equal to 0. For the moment, that is for the first span, the moment is 0.086 FL, and if you do that, let me just show you on the table. The first span, this will be, I always like this to be interactive because I would like to ask us question. Okay, let me just say this, and okay, but by the time we're in class, I will be asking us one after the other so that we will know what we are dealing with. You take it m equals to 0.086 FL, and I said our f is 50.6 as calculated the other time. Our L, which is the span, is 4.5. You get the value. Then we look at the span effective depth ratio. That's m over bd square. You can see this one, you see it's a little bit different from what we used in the other time, but for this our m, this m is this, our b is 1 meter strip. I told you 1 meter width is what you use for slab, and our d is 140. By the time you remove we said we should try 140 mm, because by the time you remove cover of maybe 25, half of reinforcement bar, maybe you will have something like 140. So I can't be doing that, but you can do that manual calculation. You have something around 140 mm. So if you do that, you have 1.06. However, this 1.06, we will now go to table 310 on our BS 8110. This is the, I have cut all the table that will be needed, but you can just look at it in your own. Now for this particular one, you can see we have FY to be equal to 500 here. So this one is applicable. Now we said we want to look at m over bd square, and it is 1.06. These are the values of m over bd square. We have 1, we have 1.50. How do we get 1.06? Even though our FY is 500, mind you, I told us the other day that we'll calculate our FS, and our FS, the value is 2 over 3 FYAS required over 3 AS provided times 1 over beta B. But if you are very observant, you will realize that some table they use 5 over 8 here instead of 2 over 3. But this recent one we are using 3 and 2 over 3. But if there's both are permitted, you can use either of the two. Now I have another table that instead of FY to be equal to 500 here, we have it as 460. That's for the old version of PS8110. It's also applicable, you can use it. So what we are going to do is we calculate our FS, and that is our design service stress. Whatever value we get, we start and substitute it to this particular one so that we get our multiplier factor. If you don't want to do that, then you can go through this table and you select what's it called, the appropriate one. You do some interpolation, but you can always use this table. It will always give you the same result. So if I calculate my FS from here, then I can put it here, m over bd squared, do the calculation, I have this. So I said note that the table is applicable for FY. This table is applicable for FY equals to this. So if we do the calculation, we have value of 1.28. Now what we are going to do is that there's something we call the limiting span effective depth and the actual span effective depth. Now the limiting span effective depth is the one that that mustn't be exceeded. That once it's higher than that, then we can't use what we calculated. So what we are trying to do is that we try to use this value and multiply it with the table I told you, table 3.9 span effective depth ratio. And I told you because this one is a continuous slab, we are taking 26, but if it is simply supported, we take 20. So 26 times 1.28 that we got here will give us 33.3. Then we are going to now check this particular value. What is the value if we use our actual span given, which is 4.5 meter, and the effective depth that we are assuming, which is 140. Here we have it to be 32.1. Since the actual one is lesser than this, then our size is okay. But if this is lesser than this, then we have to go and increase our effective depth to make sure that it is lesser than what we have there. So thus D equals to 140 mm is adequate. So after that checking, all we just need to do is do our normal calculation, calculate for them like K equals to M over BD square FCU, which is 0.035. Then we calculate our lever arm, our Z equals to 0.95D. Then we have it at our Z to be equals to 133 mm. This is your Z value. So you now calculate your AS, which equals to this M over 0.95 FYZ. Please note, the other time we have 0.87 here is the old code. It has been modified to be 0.95, but both are applicable. They are okay. If you use 0.87 or 0.95, it is acceptable. So we look for the interior support beam. We check whether the interior support beam is 100 years over BH is greater than 0.15. That is the reinforcement that we are providing. So we just go ahead with the calculation. At the end of the day, we have this is what we're going to have for our slab. This is the we calculate the transverse reinforcement 0.13 BH over 100. We have it at 221. So at the end of the day, this is how our reinforcement will be. This for the span. You do it for each. Please, whatever we have done here, this is just for this for the main reinforcement bar, which is whatever we're having here, T10 to 2 at 200. If you look at it here, we have it here, T10 at 200 for this main bar here. Sorry, for this one here rather. This is the one we treated in this our table where we selected this first moment near end span. Now at outer support or at first interior support, as first interior support we use this. Middle interior support we use this. Interior, so depending on what you are selecting, but this for the this is the one we use for the first one. You can see what we have here near the middle of end span. Now if you have any question, you can ask me on the YouTube arena or on our WhatsApp platform. So having arrived at this, you can see how you by the time you do the calculation for the span, and this is for the span, this is for the support, the span, support, like that. You do it for each one of them, then you come at you arrive at all this reinforcement bar. So it's a rigorous calculation. You can do that, you can try it, but I want you to practice it. You have to practice more so that you understand everything. Where I won't be spoon feeding you on everything. I have a lot of things to cover in this course. So in this module, so let us look at simply supported slab that is spanning in two directions. This one is very simple. What you just need to do is that we have our, as I have explained the other day, that we have our long span and the short span. And I told you that our LY is our long span, our LS is our shorter span. So if you this something like what we are talking about. So let us look at it. How do we do it? We calculate our moment along the x-axis, moment along the y-axis, and the formula for it is this for moment along x-axis, and likewise moment along y-axis. What changes between this and this is just the alpha SS and the alpha SY. So the two are almost the same. So what we're going to do is that we look for this, which there's a table for that, and that's table 3.13. You just immediately calculate your LY over LS. You have a value which must be less than 2. So you select whatever is applicable among these. You select it for alpha SS and alpha SY. So once you have done that, you calculate your moment, you calculate your N, you can calculate your N out. So you calculate this to get your N here. Everybody knows how to do this. So this is very simple. I don't need to waste much time on that, and you all know how to just substitute the value into your AS, and that will be per meter width, and likewise ASY for the moment along Y axis. Now let us now look at it. I said the slab should be reinforced uniformly across the full width in each direction, and the effective depth used in calculating ASY should be less than that for ASY because of the different depth. You know, because by the time you are putting the span, the reinforcement along the Y axis, it will be lesser because you have to remove the thickness of a slab, let me say, of the reinforcement from the depth, because this time around you will consider the shorter depth then. So at least 40% of the mid-span reinforcement should extend to the support, and remaining 60% should extend to within 0.1 length of LS and 0.1 length of YS of the appropriate support. So let us go straight to the calculation on this. We are given that we want to design the reinforcement for a simply supported slab, which is 220 mm thick and is spanned in two directions. And we're told the effective span in each direction is 4.5 and 6.3 meter, and the slab supports a live load of 10 kN per meter square. The characteristic material strength are SU equals to this and FY equals to this. Now, what I told you the other time, we calculate our LY over LS, which is 1.4. From there, once we have our FISS from the table the other time, you just go straight, calculate our self weight of the slab, which is equal to this depth multiplied by 24 kilonewton per meter cube, will give us this. Now we go straight to our N, 1.4 GK plus 1.6 QK. Now this note that I'm using 5.3 here because we are not given any other additional dead load here. But if we are doing another additional dead load, we have to sum it with this to have a total dead load now. So we have this, our N, to be equal to this. Our moment along the S-axis, by the time we multiply it out, we have this, and then we calculate our like we do our K. MSS over FCUBD square, we have it for this, and then you have your lever arm, which is Z equals to 0.95 D. You get your Z value out. You just calculate your AS, which is equal to MS S over 0.95 FYZ, and you have this. So you just use this, go and check your reinforcement bar you provide. We are providing this, so we are providing 12 mm diameter bar at 175 mm spacings, and then we go to our span effective depth ratio again, M over BD square. We look at it, what value do we have? We have 1.37. From this value, we go and check our service stress. With our service stress, we have it to be this. You all know how to calculate this. I told you that time, it's in the, I've shown you the table. So once we have this FS to be equal to 290 Newton per mm square. Now I want you to look at the next table. I want you to look at something there. You can see that we have 300, we have 250, we have this, our FS. This is our FS. But what we have here is 290. So what are we going to do it now? What we are going to do is we try to interpolate, because our M over BD square is 1.37, and that's even between this and this. So we interpolate to get the actual value for our modification factor in between, that is when our FS is 290. So you can also use the calculation. This calculation, you will arrive at the same thing. 0.55, put the FS value, which is 290, put it here, then calculate it, you get the actual value. You can also use this. This will give you the answer. But if you know how to interpolate very well, you can always look at it through here, and then you see arrive at the same thing. Now I want to show you something. This table, this is one table, this is another table. You can see here we have FY to be equal to 500 and FY is 460. So this is what I was talking about, and they are both table 310. So depending on the BSc you are using, if you are using the new version, you have this one. If you are using the old version, you have this upper one. So you just check. So once you do that, now our M over BD square is the modification factor was 1.23. Now, as I told you the other time, we look at the limiting span effective depth ratio. Now, because it is simply supported, we are taking 20 for this. Our waist slab is simply supported. But if it is continuous, we take this. So we have 20 times this. We have it with this, and our actual span, we calculated it. We got this. So we check our D is 185 mm is adequate. We do the same for our MSY. this time around the Z value will be lesser than a diameter of our reinforcement bar. That way we have 176 minus 12. The other time we have Z to be equals to 176 here. So here we are removing 12 mm from it. So our new Z value will be 164. So this is what we're going to use for our MSY. So our AS along the y-axis will differ from what we have here, from what we have in the upper one the other time. So you can do the calculation. Sorry, I think I made a little error. I will change this. This is supposed to be y. So I will change that. Please correct this in your note. This is supposed to be y. Like this is y2. Please make that correction. So at the end of the day, this is what we have, and then we're providing this, and the spacing, when you look at our spacing table, is T10 at 200 mm centers. That's what we're providing. So we now look our 100 AS over BH. We do the calculation. This is 0.18, which is greater than the 0.13 that is the minimum reinforcement for transverse steel. So this is how our reinforcement will be for the two-way slab. This is the main one, and this is the second one we just calculated. This T10 over T10 at 200 mm. This one, or this one on top. The red one is your main AS, which is your AS calculated in the for MSS, which is for this T12 at 175 mm. So that's T12 at 175 mm. So that is all about this. Thanks for the wonderful time. Please kindly ask your question if there's any question you have. Sorry for exceeding the time. I don't like using more than 20 minutes. Have a lovely day. Bye.